Okay, welcome back, everyone. So let's review what we talked about last time. We were learning about attention, which is one of the main ideas in transformers. And we learned the equations for how attention is computed. And so basically we have the ith element of the output sequence is a weighted linear combination of different input sequence elements. And those input sequence elements, what they are, you take the original input sequence element and then you transform it with a square matrix. So we have linear combination of those, and then the weights that are used for the linear combination are computed this way using inner products. And Qi is a transformed version of Xi, and Kj is a transformed version of Xj. So we can think of, regarding the weights, as when you're computing Yi, this is what you're looking for in a match. This is what the jth input provides you for that match. And then the actual value transmitted is Vj. So we have queries, keys, and values. And then this softmax operation is just a way of normalizing the weights, as is this scaling factor here. Okay, so this is how attention is computed. And to make it a bit more flexible without increasing the computation much, what they do is they chop up each of these matrices into smaller matrices row-wise. So if this is the original matrix, then they chop it up this way. In this case, they have 4 heads. And so you compute these y's of reduced dimension using this attention mechanism. So basically all these guys have reduced dimension. These have reduced dimension. And then you stack them together to get back your original embedding dimension, and you have one more learnable matrix there. And that's multi-headed self-attention. Okay. And then we said that basically the transformer blocks, so a transformer has a stack of these blocks concatenated, and the first half is self-attention, the second half is the feed-forward network. Here's the self-attention block that we just discussed, and it is surrounded by a skip layer. So the self-attention, so even if all the weights are 0, the signal still flows through. And then you have a layer norm, which acts quite a bit like batch norm, except the averaging is across features rather than across the batch. And then you have some simple MLPs. These are just 2-layer MLPs, so one hidden layer. And you typically, so each of these MLPs will process one of the input elements, or I guess whatever comes out here. Each of those output at this point is processed by one MLP. Okay, so that's the transformer block. And then we stack these blocks together to make a transformer. And then we can use it for different things, like we talked about. If you want to use it for classification, what you do is you have your word embeddings, then you add some position embeddings, because without the position embeddings, the transformer doesn't really know anything about the location within the sentence or the phrase. So you process this to an output sequence using your transformer. And then if you're doing classification, what you can do is you can just average across the whole context, get down to a single vector that has the embedding dimension, and then put that through a linear layer, so weights and bias. So you get your output logits which you could use for classification. So that's one thing you can do. And then we also have been talking about text generation. So here, the output sequence is trained, or the output is trained to try to forward predict the input sequence, but we use causal masking to make sure that when predicting this, you're not allowed to use this element of the input. So H predicts E, and then HE predicts L, HEL predicts this L, and so on. So there's a certain masking operation we use to ensure that that happens. And then we saw on our tiny Shakespeare data set that this worked quite a bit better than the other methods we had tried before. And if you scale this up using more and more computation, it just keeps getting better. Okay, so that brings us to where we are. Are there any questions about anything covered so far? Okay, so what we're going to do next is talk about some more practical real-world details, not just the toy Shakespeare example, but what happens, how are different blocks designed for in real practical LLMs. So let's first talk about tokenization and embedding again. So if you remembered, this is the process of converting, well, in the Shakespeare data set, we converted single characters into vectors. So when you work with a real LLM, you don't work on single characters. You also don't work on whole words. Usually you work on pieces of a word. So for example, the word walking could be broken into walk as one token, and then the extension ing could be another token. And so when you break things up this way, you can have like walk combined with ing or with ed or so on, and you can kind of preserve the character of walk. Okay, so there's some different tokenization methods that do that. So some pretty famous ones are byte pair encoding and word piece. So I'm not going to get into more details, but you can click the links if you'd like to learn more. But then there's the issue that some languages are not broken up with spaces between words. And so there's some other embeddings like sentence piece that tackle that. So different ways to tokenize, convert to a stream of integers. And then for the embedding part, that is pretty much exactly the same as what we talked about before. So you have some sort of vocabulary of words. We're still going to call that capital N. And you make an embedding matrix which has D rows and N columns, one for each one of your tokens. And you can extract the token for you can extract the embedding for token KI by making a one-hot coding for the integer KI, and then putting that inside, and then multiplying the embedding matrix on the right by that. And that gets you WKI, which you would use for the initial XI in your sequence to be further processed by the transformer. And then once you do the transformer processing and you end up with outputs like YI, you de-embed them by multiplying by some matrix WU with dimensions n by d. That converts the d-dimensional embedding to a vector of the size n, or the length n. And you can put in a temperature there as well to scale it. And then the softmax converts that into a PMF. And then you can draw from that PMF for generation. Now, in some models, rather than learning this de-embedding matrix, they just set it as the transpose of the embedding matrix. So it's just one less thing to learn, and in some cases that works well enough. And there's other things you can do, like so this vector will in general have all non-zero elements, but a lot of them will be very small. So if you wanted to say, let's just only consider those that have a probability of, let's say, greater than 1% or something, you can do that. You can threshold these, and then the softmax will normalize things again. And so, for example, the top P tokens, P would be some probability threshold that you can set. So there's different things you can do for the de-embedding. All right, so that's how we tokenize and embed text. Any questions? Okay, now let's talk a little bit more about these embeddings. So these are actually pretty cool. So there is a semantic meaning to every direction in the embedding space. So as a visualization, if you look at the embedding for the word king, which is this vector, and the embedding for the word queen, that might be this vector. And so these embeddings are usually in a pretty high dimensional space. This picture is kind of looking at things squashed down to 3 dimensions. There's ways you can do that. We'll talk about that probably in the next unit, like PCA. But this picture is just to try to give you the flavor of how these embeddings look. So here we have king and queen. And then if you embed man and woman, you might get these. And then the interesting thing is the difference between king and queen is also very close to the difference between man and woman. What that means is that there seems to be a particular direction in the embedding space which is corresponding to gender. Okay, so gender might be pointing in this direction, and maybe royalty is pointing in that direction. And so you get combinations of gender and royalty, and you can construct these things. Now, of course, there's more to king and queen and man and woman than gender and royalty, but at a high level, those are the relationships. And so what that means is that you can essentially do algebra on the words once they are in the embedding space. So for example, if you took the embedding for king and you subtracted the embedding for man and added the embedding for woman and looked at what you got, it would be approximately equal to the embedding for queen. Okay, so that's the key idea behind embeddings is if you have well-designed embeddings, it allows you to do just algebraic operations on them to create, and disambiguate meanings. So that's kind of the essence behind what the transformers do when they process. Another thing is, so for this little experiment here, I used the glove embedding, which is an embedding that is built as a standalone thing. It's not, it wasn't trained as part of an LLM. It's a pretty decent embedding. And if you look at the dictionary of the words most similar, or the tokens most similar to king, the 10 of the, 10 of them, or maybe 9 of them? No, 10 of them, you get these. So prince, queen, 2, emperor, son, uncle, and so on. And to get a sense for how similar they are, with 2 embeddings, you usually look at something called cosine similarity, which you can think of as you normalize x1 so that it has unit length, you normalize x2 so that it has unit length, and then you do an inner product between those 2 vectors. And because of this normalization, what you get is going to be within the interval between the numbers 1 and -1. And that's also, you might remember, Cauchy-Schwarz basically tells you that. So, this is how embeddings are typically compared. If you want to know if 2 embeddings are similar or different, you don't really look at the lengths, you look at their directions. And so this is like the numbers telling us how close prince is to king, how close queen is to king, and so on in the embedding space. Okay, so embeddings are pretty neat. I'll show you some more examples of embeddings towards the end of this unit. All right, any questions? Okay. So what attention does to embeddings, now that we know more embeddings, we've kind of discussed this before a bit, but when you look at the input to the transformer, each embedding comes straight from the code book, and so it represents a word in isolation. But then as the embedding flows through the transformer layers, it draws meaning from the other embeddings in the context and gradually becomes more nuanced. So for example, if you have the word mole in the context, at the beginning, mole can mean many different things. It could be an animal, it could be a spy, it could be a skin blemish, it could be a unit in chemistry. You don't really know what it is until you start processing it with the remainder of the context by the transformer. And as you go through the layers, you figure out, which of these things it really means in that context. Another thing that happens is there's many ideas for which we don't have a single word for. So for example, if you think about miniature Eiffel Tower, so the Eiffel Tower is like something that's really big. And then miniature Eiffel Tower, you can imagine, well, that could be a keychain or something. But that's sort of an interesting combination of two very different meanings that we don't see very often, so you never have a token for that. But you can make an embedding, and then you can combine embeddings. You can maybe add them together or something, and you can get the meaning from the individual tokens. Okay. Any questions on that? Okay. So let's think again about the multi-headed attention block. So this is the equation that we derived before. We'll write it in a slightly different way. So here we have the sum across the attention heads. And then for the jth head, for the rth head, this is what we would do. So this is basically the value, Vj, and then this is the portion of the output that is going to operate on that value. And then here we have the query and the key. But what's interesting is that if you think about how these matrices look, this is going to be a tall matrix, this is going to be a wide matrix. And so this operation here is basically a low rank matrix. And what that means is that when you go through this matrix, it projects xj onto the row space of this matrix, and then it reconstructs it in the column space of this matrix. And this is going to be a different low rank matrix for each head. And so basically each head can work on very different subspaces within the embedding. So for example, and that means you can have different forms of attention. So you might have adjectives attending to nouns. That would be like one kind of attention you get. But then another kind of attention is adverbs attending to verbs, or subjects, verbs, and objects attending to each other, and so on. And so that is what you get with, when you have different heads, you can have these different kinds of attention going on in parallel. Okay, so that is a little bit more about attention. Any questions? Okay, let's now talk about MLPs. So imagine that you input to a transformer something like Michael Phelps swims, but Michael Jordan plays, and you want it to complete the sentence. So as we know, Michael Jordan is a famous basketball player, so a decent LLM will predict basketball. And so if you think about it, that's like a very specific fact, right? That's just a fact that has occurred in our world. There's really nothing universal about the words Michael Phelps and swimming and Michael Jordan in basketball and so on. So how did the LLM actually learn this fact? Where did it store the fact? So it seems people think that the MLPs are where these facts are stored. And you can actually see how this can happen if you look at maybe constructing kind of a contrived example, and then looking at what happens in the MLP, which is actually something that's like a very simple equation since it's just a 2-layer MLP. So for example, let's say that the embeddings for Michael, we'll call it X Michael, for Jordan, for Phelps, and for basketball, let's say that these are all orthonormal, meaning that at the beginning, these things really have nothing to do with each other. They're just mutually orthogonal concepts. And let's say that we'll define XMJ as the embedding from X Michael plus the embedding for X Jordan, okay? And then we'll say XMP is X Michael plus X Phelps, all right? So this embedding here has combined Michael and Jordan, and XMP has combined Michael and Phelps. And now let's say that we've trained our MLP, and if you remember, this is the equation for it. So this is the input layer, the activation, and the output linear layer. And because there's a skip connection, it's the input, plus this whole effect of the MLP. So this UJ would be for the jth activation, and usually these architectures, the number of activations they use is 4 times the dimension of the embedding. So these are the different rows in the input weights, or the input layer weights, and we have an input layer bias, and then this is the jth row in the output weight, and so the effect of the MLP will just be a sum over all of those of this stuff. So essentially, remember that the ReLU passes anything positive and sets to 0 anything negative. And so, and basically for this to be positive, you need that this part is greater than this bias, right? So you need that this inner product UJ transpose XI is greater than the bias J to get a non-zero ReLU output. So basically, this UJ acts like a question. That it's a question you're asking of XI, and BJ is like a threshold for the yes-no. So this is like a yes-no question. And BJ is a threshold for how high does that thing need to be to consider it a yes, otherwise it's a no. And then, if it is a yes, meaning there's something that was positive and came through the ReLU, then this is what you will add to XI. And if it's a no, then the ReLU will output 0 and you won't add anything to XI. Okay? So let's say that we're putting XMJ through our MLP, so that's what XI is. And we said that this, let's say I1, we're looking at the very first activation. The very first activation is also XMJ. So the question is like, are you Michael Jordan? It's basically what this is asking of XI. And if it is Michael Jordan, then this, because we said they're orthonormal, this would be 1, right? And so this bias just needs to be something, the bias might even be 0 in that case. I think, here I chose it as -1. So basically, if it's Michael Jordan, something comes through the ReLU, and then what we can do is we can set basketball, X basketball could be VJ, and so if XI is Michael Jordan, you add basketball to it as it flows through this MLP. Right? But what if it's Michael Phelps? So when you ask this question of Michael Phelps, you're not going to get as big of an inner product. Let's say it's below the threshold BJ. In that case, you would get nothing out of this stage, and so you would not be adding basketball to Michael Phelps. Right? So that's basically just concretely how you can imagine these MLPs storing facts. You could also have maybe the next vector, the one that is tuned to Michael Phelps could be, are you Michael Phelps? And then if so, V2 could be X swim. So if it's Michael Phelps, you add swim to that, Michael Phelps, to enhance its meaning. And now you know that that this thing is has a component for Michael Phelps and for swimming in it. Okay, so does that make sense as to how we can kind of store facts? Yes?
Sorry. Why is it 4D again?
This is a practical choice that is very popular. It doesn't need to be, but a lot of the architectures, from the beginning, that's just what they assume. They had to choose the number of activations.
Oh, they just chose.
And they just chose 4 times the input and output dimension.
Gotcha.
Yeah.
What you said, BJ?
Everything is learned,
Okay.
right? So everything, yeah. So the V's, the U's, the B's, those are all learned things. So it's as you pass tons of training data through, the training data is going to implicitly have this connection between Michael Phelps and swimming, Michael Jordan and basketball. And then when you're trying to predict sentences that have those words, you will see that this is useful information to store in your MLP. Yeah, everything's learned. Okay, good questions. Any other questions? Okay, so there's something that's even a little bit more interesting that's going on here. This kind of viewpoint that we've discussed on this page, if you think about this sort of question-answer thing, it's easy to understand this with different questions. Let's say, different questions could be in different subspaces. So, this you would have these are U1, U2, U3. So, this is are you this person? Are you that person? Are you this thing? And so on. And if you think about it that way, then the number of different questions you could ask would be 4D, right? 4D different questions. But you're actually working only in a D-dimensional space. And so really to have these orthogonal, you could actually only have D different orthogonal questions and answers in this D-dimensional embedding space. And that's not very big. So, so let's say for GPT-3, which is one of the big famous models, the one that was essentially used for ChatGPT, they use an embedding dimension of 12,000, or 12,288 in particular. And so that suggests that you could only have, 12,000 different facts stored, which is really not enough to describe things in our world. So, but it turns out things don't work exactly like that. So while a D-dimensional space contains only D exactly orthogonal vectors, it contains many more nearly orthogonal vectors, especially when D is large. And there's something, a mathematical concept called the Jordan-Lindenstrauss lemma, which basically says that the number of vectors that are within theta radians of being mutually orthogonal is this. So here's the dimension, D. This is some number, C, which people don't know exactly, but they've done some work to try to figure out what it is. And then sine of theta squared. So if you insist on being exactly orthogonal, then theta would be 0. But if you allow things to be within 1 degree, so between 89 and 91 degrees, then you would set theta to be whatever 1 degree is in radians. But the important thing is there's this exponential here. So the bigger that you allow theta, which is how much you can depart from perfect orthogonality, the bigger f gets. And if we plug in some numbers, so you can prove that c has to be less than or equal to 8, but people think it's actually closer to 0.2. So if you plug in 0.2, and for d you plug in this GPT-3 dimension, and then you look at for different thetas and degrees how many facts you can store. So 1 degree from orthogonality, perfect orthogonality, 1.3 times 10 to the 8th. So what is that, like 100 billion? If you allow 2 degrees, now you can go up to 10 to the 32. If you allow 3 degrees, now you can go up to 10 to the 73rd. So massive numbers. And so this basically says that these MLPs, if you don't insist on the facts being completely orthogonal but related to each other, you can have an enormous number of facts stored, which is pretty cool.
And theta is not like it's not a hyperparameter, is it? It's just like a fact.
So this is just kind of a mathematical analysis of interesting things that happen at high dimensions, because we can visualize things in dimensions 2 and 3, but there's interesting things that happen in higher dimensions that are hard for humans to visualize, but then you can often maybe prove something mathematically about them. So the question here is, I have a d-dimensional space and I want to pack in exactly orthogonal vectors. How many can I fit? Well, we know it's d. What if I allow those vectors to be a little bit not orthogonal? How many can I squeeze into a space? And that ends up being this number. And that number, if you allow just even a little bit of orthogonality, is a massive number as d gets larger. Because you can see d also needs to be large for this really to grow. So if d is very small, then you don't get this benefit. But as d gets larger and larger, you get this massive benefit from little deviations from orthogonality.
So is d the number of vectors?
D is the dimension of the embedding space.
Okay,
Always.
so is there some kind of discretization of the vectors? Because if they were continuous, I would think you could have infinite vectors.
Yeah,
that
you
are close.
You can have infinite vectors. The question is, if you have distinct facts, what are distinct facts? How do you describe them? So if they're absolutely perfectly nothing to do with each other, they would be orthogonal in the embedding space. What if they're these two facts are just a tiny bit related. They both relate to some subject. Now they're not going to be totally distinct. So they're not going to be 90 degrees apart in the embedding space. They're going to be, a little bit less than 90. And so the question is how many of these distinct yet not completely distinct facts can I squeeze in for a given embedding dimension?
Yeah, so if you have two that are not orthogonal and another pair, or let's say one vector and then two that are very close to orthogonal, if they're close enough to each other, it doesn't count that as one, or it does count as just a singular fact and not two.
Because I didn't quite understand the question again. So let's say I have a bunch of vectors and I'm allowed to make them 89 degrees, so not perfectly orthogonal, 89 degrees apart from each other. And the question is, how many can I squeeze into this space so that they're all mutually 89 degrees from each other, or larger, or closer to 90?
Okay.
Yeah. So they're all distinct from each other. So when we talked about 3 dimensions, you have these three. You have 90 degrees, 90 degrees, 90 degrees. So they're all mutually orthogonal. In 3 dimensions, if I allow 89 degrees, I can't fit in another vector. You can just kind of imagine, I can move this over a little bit. I can move this over a little bit anywhere, but I don't have enough freedom to stick in a whole nother vector. It's just not big enough. But as you go from 3 to 4 to 5 up to thousands of dimensions, then there's enough room to squeeze in more vectors and keep them mutually orthogonal to all the other vectors, or almost mutually orthogonal. So that's the idea behind this Jordan-Lindenstrauss lemma.
So that's why in the previous example, we assumed that all of them were orthogonal.
In this previous example, just to make the math very simple and clean, we assumed everything was exactly orthogonal. Yeah. Because like, if you do that and you use exactly this construction, you can trace through and you can see exactly what's going to happen. And it's going to, it will give you a certain very clear behavior with Michael Jordan, a very different clear behavior with Michael Phelps. And it kind of makes sense that, Michael as a concept is pretty orthogonal to Jordan as a concept, like in general. And then Phelps is another, pretty orthogonal concept, and then basketball is another one. But if you want to start combining Michael Jordan and basketball, you can add those embeddings together, and now you can get this new embedding that's not in the original dictionary, but it draws meaning from all those original atoms and is now like a new thing that has, all those meanings together. Michael Jordan, basketball. That's what the transformer does, is it starts packing these things together, giving you vectors that are not in the original dictionary, but which have important, distinct meanings in our language. Because our original dictionary is also, this is not something we can make extremely large. We'll see some numbers, but it might be like 50,000 or something, different tokens. But the number of distinct facts in the world or concepts in the world is way bigger than that. So we can do that by taking these 50,000 different embeddings that we start with and then adding, subtracting them. And now you can get just different vectors in this d-dimensional space. But the question is how different are they? How orthogonal can you make them? Well, we see that you can actually make tons and tons of almost perfectly orthogonal things within a big space. Yeah. Huge numbers. Okay, good questions. Any more questions?
This is kind of going back
Sure.
a little bit, but with tokenization, you have these specific tokens. What if somebody inputs like a misspelled word, and it's not one of your tokens? How do you deal with that, or is that just kind of out of the?
There's different ways to deal with that. Because the tokens are usually subwords. Like if it's like something that doesn't exist, but then it has like an ing extension. So for something that is absolutely unknown, you can have like a token, which means I don't know.
Oh, okay.
And then you can combine that with ing, which makes it sound like it's kind of a verb. It's like some kind of verb, but I don't know.
And then use the rest of the sentence to fill in what this should have been.
Exactly. Yeah. So that's what happens is it starts out not really giving much information to the other tokens, but then it accumulates meaning from the other tokens and gets disambiguated to the sense like where you're reading something and you realize this is misspelled, but you can figure it out from the context.
Gotcha.
The same thing happens. Okay, good. Any other questions? Yes.
I'm just curious, how do you, for instance, I don't know, differentiate between, in this case, let's say Michael Jordan, the player, from Michael Jordan, the actor, So all of these combinations will be that allow the machine to differentiate and establish on context in the problem.
Yeah, it's exactly this kind of same way that we've been describing. So you have this context which has a lot of information that helps you understand which Michael Jordan we're talking about, right? But the only way to get that meaning is to process the whole context with these transformer blocks. And what they do is they do algebra in this embedding space. And so there's going to be other words in the sentence, that have to do with acting or movies or something that are going to eventually, as you process through these layers, they're going to be put into the Michael Jordan. And now that Michael Jordan will have this acting component rather than the basketball component. And so there could be some facts in the MLP, the same like what we discussed, where with some other context, you can figure out that this is actually the actor and not the basketball player. Yep. Okay, good questions. Anything else for now? Okay. So then you might wonder, well, okay, these modern language models, they actually do more than language these days. They can handle images, they can handle speech, and they're called multimodal models. Modalities, different modalities means, different flavors of information, text, images, audio, and so on. And so if we're going to work together with these in a model, we have to be able to tokenize and or embed these different sources of information. So then what do we do for images? So there's a number of different things you could do for images. So when you look at the original Vision Transformer paper, which was the first paper that really said we can process images using transformers. What it did is it broke up the image into small 16 by 16 patches, 16 pixels by 16 pixel patches. And for each one of those, which is now a 256 length vector, you don't have to tokenize it. You can create the embedding directly with some linear stage. So you do some matrix multiplication, and you add a shift, and C and B can be learned parameters. So now every 16 by 16 patch gets mapped to an embedding of a size that you control. So C could be a wide matrix, in which case the embedding could have less than 256 components, or C could be tall, in which case the embedding actually has a larger dimension than the number of pixels in the patch. That's a design choice. But anyway, that accomplishes embedding without tokenization. It just goes directly there using this linear stage. Is that idea making sense? So basically, let's say you were working with data that was your own data. It was maybe, stock market data or something. It's not images, it's not language, it's not text. You just have like a stream of vectors. So you want to get that into your transformer to process them. So if this is a multidimensional vector, which it really needs to be to use a transformer, you would choose an embedding dimension, and then you would learn matrix B and an offset B to get your embeddings. So this is just something that you learn for whatever task you're doing. Maybe it's regression, maybe you're predicting for it. So this is a form of embedding that works for anything that doesn't do any tokenization. It just skips that step. But there are ways, there are actually better ways than this, because this is not very sophisticated, it's just a linear stage. You can do something more sophisticated. And so currently, probably the most popular approach is something called vector quantized variational autoencoder. And so there's a few parts to this. The first stage is to put your entire image, so this is going to be something of dimensions height by width by 3, because it's red, green, and blue channels. So it's a tensor, you could say. You put it through an encoder, and essentially what this encoder does is it transforms this image to what's called a latent representation, which is another version of the image that has typically smaller spatial dimension. So you would have like a downsampling factor of D. So let's say D is 4. So that means you're now going to have h over 4 height and w over 4 width. So the number of pixels is now reduced by a factor of d squared, or 16. But in order to kind of accommodate the fact that you have lost spatial resolution, you can grow the number of channels from your original RGB to some larger kind of abstract space of C channels that don't necessarily have to be red, green, blue. They can just be, something extra. And basically, by controlling D and C, you can change how many numbers, how much compression you have going from I to Z in the sense of just how many numbers you're encoding the image with. And usually you can sort of compress things down by a pretty good amount without losing much quality through this encoder. And then you can also build a decoder that starts with this Z, and from it reconstructs the image. So this is what VAEs do. It's a kind of network that squeezes information down into a more dense, efficient representation, and then unsqueezes it with hopefully as little loss as possible. So that's the VAE. But now what you do is, after you squeeze it down to Z, then what you can do is you can quantize it using something called vector quantization, which is just basically to make a code book, here again of n elements, and quantize each one of these C dimensional pixels. So you can think of this as you have now h over d times w over d pixels, but your channels, you have more than 3 colors now. You have C colors. So we can just make, for each one of these pixels, which is a C dimensional vector, we can learn a code book with n different n different possibilities. So this is like a way of quantizing that C dimensional space as n different vectors that can be learned. And then we just do this simple quantization where if you put in Zi, you look for the closest vector in your code book. That's what this argmin does. And then once you find which one that is, you just store it by its integer. You say oh, this is closest to the 3rd element in my code book, so now I'm going to represent Zi just by the number 3. Okay, so you encode, quantize, and then if you have a big enough code book, you don't lose too much, and you can reconstruct your image. So this part is now tokenization. This VQ is tokenizing, it's making your data discrete in the middle. Okay, so this is a bit of a more mature approach to how you tokenize and embed images. Today's models actually could jointly embed these things. They have representations which are combined image text. So, and maybe speech as well. Okay. Any questions on that? Okay, so we discussed a lot of the kind of high-level concepts of these language models. And let me see. So what I was going to do next is to kind of lead you through sort of just historically how these things evolved, so you can see how the numbers have scaled and how the concepts have changed over time. So let's start with the original transformer from Google's paper, Attention is All You Need. So we've talked about this paper before. And now we're going to actually look at the structure of their model. So this paper was focusing on machine translation, going from one language to another. So they have kind of a more complicated transformer than what you need for text prediction or classification. And it looks like this. So you have information coming from one language into this left path. And this part looks just like what we learned. So you take your inputs, you embed them, you add positional encoding, you go through your multi-headed attention, your layer norm, your feed-forward network, your layer norm. Okay. The only difference is that you are not using causal masking here, because your goal is not to predict forward one token at a time from your original language. Your goal is just to come up with a new output sequence that has somehow boiled down the meaning of this original language into a new sequence. And that, you can call this a latent vector. That latent vector is coming in the middle of this decoding network. This is called the encoding network, and this is called the decoding network. The decoding network is doing generation. It is doing token by token generation, autoregressive. And so this one is trained the way we described with a masked multi-headed attention. So these are the two layers we talked about. But now it is doing two things simultaneously. On one hand, it is trying to generate text in an autoregressive way. So whatever inputs you have here, you are trying to predict one word forward, just like we've talked about. But there's an added constraint, is that whatever you are predicting should have the meaning of the text in this language. And that meaning has been stored in this latent vector. So there's this one other attention head here, which is doing what's called cross-attention, not self-attention, as we've been discussing. So what cross-attention is doing is it's taking in this information as well as this information and merging them. Okay, so this is what you need to do if you're doing translation, but it's not what you would need to do for generation. Okay. So this is doing generation, but with meaning coming from another source. Is this idea kind of making sense? Any questions?
The inputs on the right side, output embedding, or output shifted right, and not also just inputs.
So this is like, say, in French.
Oh,
Okay, and then let's say we're translating French to English. So basically what we have here is we have a few words of English, and then now we're shifting them in time, trying to predict, as we do for generation, we try to predict a shift. Does that make sense?
Input is in French. Where are the few words of English coming from?
So let's say to initialize, you might initialize this with like nothing. So maybe like carriage returns or spaces or something. So when you start, you're not really, there's nothing coming in. But let's say you've kind of put your language through here. So now you have some meaning. And and this is done over various stages. There's n stages of these. So essentially you start with like an empty sentence, and now you're trying to predict the first word in the sentence, which is going to be the shift. And you're doing that saying, well, the first word has to be consistent with what I said in French. And then, and then you're doing this autoaggressively. So now the next word you're trying to predict forward, and the next and the next.
Oh, okay, I see what you're saying.
Yeah. So in some sense, like this is exactly what we talked about for word generation. But now we're adding, in addition to the outputs being a shifted version of our inputs, they also have to be consistent with this extra information that we got from another source.
Gotcha.
Yeah. Okay, is it making sense? All right. So people call this the encoder network, the decoder network. The encoder network generally does not use causality because it is just trying to understand the sentence or the context as a whole. It's just trying to, boil it down. Decoder networks have this masking because they are used for autoaggressive text generation. So keep that in mind. So the first OpenAI model called GPT, Generative Pre-trained Transformer, was from June 2018. And at the time, most of the natural language processing models were trained on manually labeled data. So people had to manually label data and stuff, which is expensive, and so there wasn't much data. And what was novel here is they proposed to pre-train on next token prediction, as we've been discussing in this whole unit, which enables the use of large unlabeled data sets, just text from the internet, and then fine-tune on a desired target task, like classification or translation or whatever you want to do. So there's now 2 stages. Pre-training, which is just as we've discussed, but then there's a whole nother kind of training stage called fine-tuning, where you turn this thing into a chatbot. You go from a next token predictor to a chatbot. So we'll talk about the fine-tuning a little bit later, but it's like a whole nother stage of training. But generally, it's not as intensive. You don't need massive data sets. You're just kind of tweaking what you learned from the pre-training stage, where you might have used like everything you could get on the internet. Okay. So this, what's special about GPT, this whole idea, and OpenAI and these models, is that they were the first people to kind of figure out that we can pre-train on just massive text and then specialize it to do interesting things like have a conversation or code or do other things. Okay, so that was the first GPT. So byte pair encoding with 50,000 tokens, decoder-only model, so autoregressive, with 12 transformer blocks, 12 attention heads per block. Embedding dimension was only 768. Context length was 512 tokens, and it had 117 million parameters. And they trained it with the book corpus dataset, which had 7,000 unpublished fiction books, about 1 billion words. And this took approximately 1 petaflop per second days. This is the way that people tend to quantify computation. So a petaflop per second is like, it's kind of like a unit of compute that you can get with maybe several GPUs working simultaneously. And then it's like running that amount of computation for a single day would get you 1 petaflop per second days. And so at the time, this cost them about $50,000 to train. Okay. Let me just talk about BERT and then we'll stop. So then, just a couple months later, Google came out with BERT, bidirectional encoder representations. And what's different about BERT is they use an encoder-only model, a bidirectional model. So whereas GPT was always doing next token prediction, BERT says, no, let's do this. Let's predict a random masked word in a sentence, and let's predict whether one sentence follows another. So they're kind of using this architecture, so no causal masking. They've just kind of changed their objective of what they want to do. And this also worked quite well. They used word piece tokenization, similar vocabulary size, a little bit smaller, similar overall size. Well, let's see, 24 transformer blocks, 16 attention heads, 1024 embedding dimension, 512 context, 340 million parameters. So yeah, about twice or 3 times. And they used, but here's the difference, 250 billion tokens versus 1 billion tokens. So a lot bigger data. Taking 6 petaflop per second days, so instead of 1, 6 times as much, but costing 7K, which is less than the 50K. So why is it less, do you think, than 50K? Well, this is more. Yeah, this is 6 versus 1. So 6 times as much compute, but was cheaper. Why is that? Why do things get cheaper over time? compute-wise.
Hardware improvements.
Hardware improvements, exactly. So as you go, you'll notice that like the numbers keep going up, but sometimes the costs go down because the hardware improved. So now to do the same thing would be a lot cheaper. In fact, if you did this today, it would probably, I don't know, probably cost like $10 or something. It's just at the time, that was a lot. Back in 2018, you had to have a lot of hardware to do it. Today, you could do the same thing very cheaply. Okay, so that's where we can stop. But I just kind of wanted to point out like the fact that you can train these things in different ways. You can train them to predict a missing word, or you can train them to predict the next word. It really just depends on the model. Okay, so we'll stop and we will continue next time. See you guys later.